the story we have been told about the universe's genesis might be a cosmic fabrication. A new theory dares to question the ultimate origin, suggesting that the Big Bang wasn't the starting gun. When the James Webb Space Telescope, JWST, beamed back its data from deep space, it did more than capture awe-inspiring images. It sparked a quiet revolution in cosmology. Among the most sensational findings to ripple through the scientific world was the detection of what appeared to be over 750 ancient galaxies, some appearing more massive and structured than expected at such early cosmic times. The implications were seismic, and few figures captured the magnitude of this potential paradigm shift more provocatively than theoretical physicist Michio Kaku, who suggested that these discoveries may challenge existing models of early galaxy formation and prompt refinements to the Big Bang theory. Before we start, please like and subscribe for more updates. At the core of the Big Bang theory lies a singular proposition: that the universe began as an infinitely dense point some 13.8 billion years ago and has been expanding ever since. All observable matter, time, and space supposedly emerged from this primordial singularity. It's a framework supported by cosmic microwave background radiation, redshift patterns, and the relative abundance of light elements. But the JWST, with its unprecedented sensitivity and resolution, has provided astronomers with data that doesn't neatly fit into this long-held narrative. What caught scientists off guard was not just the number of galaxies JWST uncovered, but their age and structure. These galaxies appeared to be mature, massive, and well-organized, traits they shouldn't have had at such an early stage in cosmic history. According to existing models, galaxies need billions of years to grow into complex systems with defined spiral arms and galactic bulges. Yet, the Webb telescope identified hundreds of galaxies that, by redshift analysis, existed just 300 million years after the supposed birth of the universe. That alone would have been startling. But then came the real shocker. Spatial measurements and light distribution patterns indicated that many of these galaxies appeared to be more developed than expected at such early times, challenging our understanding of cosmic evolution. To understand the gravity of this discovery, it's essential to grasp what the observable universe means. It's not a hard physical boundary, but a limit defined by the speed of light and the age of the universe. Because light takes time to travel, we can only see objects whose light has had time to reach us. In theory, that makes our observable universe about 93 billion light-years in diameter. But if galaxies are being observed with characteristics that challenge our timeline, it suggests something fundamentally flawed in our model of spacetime, or perhaps in our understanding of cosmic expansion. Michio Kaku, known for his work in string theory and his ability to translate complex physics into accessible ideas, was quick to seize on these developments. He emphasized that if these findings hold up to scrutiny, they could challenge the foundational assumptions of early galaxy formation. In his analysis, Kaku outlined several key implications. First, the idea that time and space began at a singular point may require refinement. Second, the universe may not be expanding from a single origin point, but could be part of a far more intricate, possibly complex structure. And third, if galaxies appear more advanced than our models predict, then either our tools for measuring cosmic distances and ages are flawed, or the universe's early evolution is more complex than we have ever imagined. This reevaluation doesn't come lightly. The Big Bang theory has enjoyed near-universal acceptance for decades, forming the backbone of modern cosmology. Yet, it's always been a model with known gaps. The theory struggles to explain why the universe appears so uniform in temperature despite its vastness, why inflation occurred at the rate it did, or what happened in the moments before the Big Bang. Questions often shelved for future exploration. But the Webb telescope's revelations have made those questions more urgent and more difficult to ignore. Some interpretations of the JWST data suggest that the Big Bang may not have been a unique event. The detection of mature galaxies so early in the universe's timeline hints at a universe that may have formed complex structures faster than expected. This notion aligns with hypothetical cyclic or bouncing universe models in which the cosmos undergoes endless cycles of expansion and contraction. In these frameworks, what we interpret as a Big Bang might simply be one of many such events in an eternal timeline. If this is true, then time itself did not begin with the Big Bang. Instead, our universe may have inherited structural information or matter from a previous cosmic cycle. That would neatly explain the unexpected maturity of those early galaxies. Some of them may not be early at all, but rather remnants or reincarnations of previous cosmic epochs. In this context, the discovery of 750 galaxies with unexpected complexity becomes more than an observational anomaly. It becomes a window into a potentially more intricate universe. Kaku also highlighted the potential implications for our understanding of dark matter and dark energy. If galaxies appear more developed than expected, then perhaps dark matter is not simply a mysterious halo surrounding visible galaxies, but part of a broader cosmic framework. Similarly, dark energy, credited with accelerating the universe's expansion, might be a misunderstood consequence of a larger multidimensional structure. The observable effects we attribute to dark forces may, in fact, be shadows of a deeper, more complex reality, playing out in ways we don't yet fully understand. Further complicating matters is the geometry of the universe itself. If these galaxies are more complex than our models allow, then the universe may not be flat or uniformly curved as previously assumed. Instead, we may be peering into vast, warped regions of space-time, regions that loop or twist in dimensions we cannot yet perceive. This notion finds some support in string theory and brain cosmology, fields where Kaku has spent decades of research. These models propose that our universe may be a three-dimensional membrane floating in a higher dimensional space. And what we observe as expansion could be motion through those hidden dimensions. The unexpected complexity of early galaxies also forces scientists to revisit the concept of cosmic inflation. According to inflation theory, the universe expanded faster than the speed of light in the first fraction of a second after the Big Bang, ironing out irregularities and creating the smooth, homogeneous cosmos we observe today. But the mature state of these early galaxies suggests that inflation may not have occurred uniformly, or perhaps not at all in the way we think. If inflation failed to erase all prior structure, then relics from a pre-inflationary phase could explain the anomalies detected by JWST. Some theorists have even floated the hypothetical idea that we may be observing phenomena that challenge our understanding of cosmic boundaries, perhaps hinting at a multiverse. This would suggest that the Big Bang was not a singular event, but one among countless others, each birthing a different universe with unique physical laws and properties. The detection of these 750 galaxies may then be the first empirical hint that our universe's early evolution is more complex than current human comprehension allows. It's not only theoretical physics that must adapt to this shifting landscape. The field of observational astronomy faces its own reckoning. If the instruments aboard the James Webb Telescope can detect galaxies with unexpected properties, then either our cosmological models are incomplete or galaxy formation behaves in ways we have yet to theorize. The tools and algorithms used to estimate distance and age based on redshift may need recalibration, or entirely new models may be required to interpret what JWST is actually seeing. Of course, these findings have implications for the origin and fate of the universe. If the Big Bang model requires refinement, then the question of origin becomes not just philosophical, but practical. What came before? What shaped these early galaxies? If, indeed, the universe's early evolution was more complex, and more intriguingly, what comes next? A cyclic universe might suggest eventual contraction, leading to another big bounce. A multiverse might mean endless creation with no singular destiny. Michio Kaku's interpretation doesn't claim to have all the answers, but it opens the floodgates to inquiry. His framing invites scientists and thinkers alike to reevaluate sacred tenets of cosmology. If we refine the Big Bang as the definitive origin, we liberate ourselves to explore models where time loops, universes spawn in complex patterns, and space itself is a living, dynamic organism. This is not the death of cosmology. It is its renaissance. As data continues to flow in from JWST, each transmission carries the weight of potential revolution. The telescope was designed not merely to see deeper into space, but to pierce the veil of time. What it has uncovered so far suggests that the universe is not just stranger than we imagined. It is stranger than we can imagine within the old frameworks. The galaxies it has revealed aren't just objects. They are messages from a cosmos that may be more complex than anything the Big Bang model ever accounted for. For now, the detection of 750 galaxies with unexpected complexity remains both a scientific marvel and an intellectual challenge. It is a call to revisit fundamental questions with renewed curiosity and skepticism. Theoretical physicists, cosmologists, and astronomers will spend years, perhaps decades, debating, testing, and refining the implications. But one thing is certain: the story of the universe is far from settled. And the James Webb Space Telescope has just turned the page to a chapter we never expected: the discovery of over 750 galaxies with unexpected complexity is not merely an extension of previous observations. It represents a frontier that redefines the limits of human understanding. As more data is analyzed, a clearer picture begins to emerge, one that reshapes not just the theories of cosmic origin, but also the structure and composition of the cosmos itself. The deeper implications extend well beyond the initial shock, penetrating into realms of physics and philosophy that have long been speculative or out of reach. One of the most profound consequences lies in the shifting interpretation of cosmic time. In a universe governed by the Big Bang, time has a starting point, an origin moment when everything began. However, if galaxies existed in an organized and evolved state earlier than expected, then the arrow of time itself must be reconsidered. The presence of complex systems at such an early epoch suggests either an accelerated timeline for structure formation, or that time did not behave as expected in the early universe, or that what we call early isn't as straightforward in a more expansive temporal framework. This raises a concept that until now has belonged mostly to the theoretical realm: time asymmetry across different regions of space. In traditional cosmology, time flows uniformly throughout the universe. But what if, in reality, it flows at different rates in different regions? Or worse, what if what we perceive as the beginning is a localized phenomenon, while other areas of the universe or hypothetical multiverse follow different temporal rules entirely? The galaxies detected by JWST could represent areas where galaxy formation evolved faster, leading to earlier complexity than what occurs within our observable bubble. The idea of cosmic variance, typically used to describe the slight variations in the cosmic microwave background, now takes on an entirely new dimension. Instead of tiny fluctuations in temperature and density, we might be dealing with entire cosmic domains whose properties, gravitational, temporal, dimensional, differ dramatically from ours. This would mean the observable universe is just a patch within a larger, richly textured expanse where the laws of physics may vary. One immediate implication of this is that the search for a so-called theory of everything, a unified framework that ties together gravity, quantum mechanics, and all known forces, might be inherently complex. If different regions of the cosmos operate under varying physical laws or constants, then the notion of a single unifying principle may be more of a human intellectual construct than a reflection of cosmic reality. This shifts the burden of proof onto physicists to not only find mathematical coherence, but to accommodate variability, adaptability, and potentially even contradiction within the universe's larger structure. Such ideas echo the philosophical underpinnings of string theory and M theory, where multiple dimensions and brane worlds allow for a hypothetical multiverse in which different pocket universes follow distinct physical rules. Michio Kaku has long advocated for the validity of string theory's higher dimensional frameworks, and the JWST findings breathe new speculative life into those ideas. The galaxies with unexpected complexity could be consistent with such complex frameworks, their light-revealing processes we don't yet fully understand. Moreover, this discovery reopens the conversation around cosmic topology. The universe, long assumed to be flat or nearly so, may actually be far more dynamic and intricate in its shape. If the cosmic web produces complex structures earlier than expected, it's possible that the universe has a more intricate configuration. The implications of a complex universe could explain why some galaxies appear more developed, or why light from a singular source might reach us in unexpected ways. This has already been hinted at in gravitational lensing phenomena, but the scale proposed by these new findings is vastly more ambitious. Another critical consideration brought on by this discovery is the nature of light itself and its journey across vast cosmic distances. Light is our primary tool for observing the universe. Its redshift is used to estimate distances and determine how fast objects are receding due to cosmic expansion. However, if these 750 galaxies are more complex than we believe possible in 13.8 billion years, it calls into question either the accuracy of our redshift models or our assumptions about galaxy formation across different cosmic conditions. This opens the door to exploring fundamental physical constants. What if the processes governing galaxy formation have varied over cosmic time or under different conditions? Though this has been considered speculative within standard physics, there are models that propose varying conditions as a solution to cosmological paradoxes. The galaxies observed by JWST may provide the first real data to test these radical theories. If our assumptions about early universe conditions are not universal, many of our measurements, such as distances, ages, and rates of expansion, may need refinement. Another avenue of inquiry lies in quantum entanglement and the possibility that distant parts of the cosmos are connected in ways we don't yet understand. Quantum physics already challenges locality through phenomena like entanglement, where particles separated by light years affect each other instantaneously. On a cosmic scale, there could be networks of entangled systems influencing the distribution and behavior of galaxies, meaning that what we observe as structure could be the surface manifestation of much deeper, non-local connections. The idea that the universe is a hologram, a projection of information encoded on a two-dimensional surface, gains renewed relevance if galaxies appear more complex than they should. This might suggest a need to rethink how information is encoded and processed across the cosmic substrate. Some theorists posit that these apparent galaxies with unexpected complexity might be artifacts of our limited observational instruments, prompting new questions about how we interpret cosmic data. This shifts the entire discussion from material cosmology to informational cosmology, where the universe is not a thing, but a process, a computation unfolding in complex ways. Additionally, the possibility that we are witnessing the gravitational influence of unseen structures adds yet another layer of intrigue. If the JWST is detecting objects whose properties cannot be accounted for by standard models, perhaps those effects stem from within our universe's complex dynamics. In some models, unseen structures can influence galactic distribution or accelerations, which might match the unusual arrangement and motion of the galaxies JWST has detected. The sociological and intellectual impact of these revelations is also profound. For decades, astrophysics has operated within a framework that, while expansive, was ultimately self-contained. There was an origin, a structure, and a fate. Now those certainties have been cracked open. Students, researchers, and thinkers must now entertain questions that were once considered speculative fiction. Are we in a unique universe? Is our universe one of many hypothetical domains? Do we occupy a privileged or peripheral space within a vastly more complex hierarchy of reality? These questions are no longer purely philosophical. They will begin to influence the design of future telescopes, the priorities of space agencies, and the funding of new research into exotic physics. Missions will be planned with an eye toward detecting what lies within our observable cosmos, perhaps even attempting to map influences from complex cosmic structures. Entire fields may arise to study cosmic archaeology, not just of our universe's past, but of its connections to broader frameworks. Artificial intelligence, too, will play a greater role in parsing the massive data sets required to track and analyze galaxies at this scale. Already, machine learning is being used to identify patterns in galactic formations and light curves that human eyes might miss. With thousands of potentially anomalous galaxies to study, AI will become essential in detecting the faint signatures of exotic phenomena or previously unknown cosmic processes. The discovery also rekindles ancient human questions under a new scientific light. What is our place in the universe? Are we alone? Not just in terms of life, but in terms of our universe's architecture. The religious and metaphysical interpretations of creation, once comfortably nestled within or parallel to the Big Bang narrative, must now contend with the possibility of a more complex cosmic history? And what of the nature of reality itself? If our understanding of space, time, and matter is this incomplete, then perhaps even our definitions of what it means for something to exist need revision. The galaxies JWST has uncovered could be part of a deeper layer of reality, what some theorists call the metaverse. Not to be confused with the fictional metaverse, but a level of existence that contains complex cosmic constructs. In such a view, our universe might be one page in a larger book, and JWST has just shown us a glimpse of the next chapter. It's also worth considering how this discovery might influence the future of space exploration. If regions of the universe exhibit unexpected complexity, then the possibilities for travel, communication, or even habitation in those regions might differ radically from what we expect. Exotic phenomena like wormholes, time dilation, or quantum tunneling, long considered theoretical curiosities, might be essential mechanisms in navigating a cosmos that is more complex than we thought. Humanity's future in space, from colonization to advanced research, might hinge on understanding these far-flung galaxies. The ethical considerations are just beginning to be discussed. If we are on the verge of discovering not only more of our own universe, but possibly its broader context, what responsibilities do we hold? Could there be forms of life, intelligence, or even civilizations in those realms? If so, how do we interpret our role in that greater expanse? The idea that we are not the center of the universe is centuries old, but this new revelation suggests we may be part of a far more intricate cosmic story. The universe, or broader cosmic framework, is no longer a static canvas, but a living, dynamic continuum, one that stretches, folds, and evolves in ways we are just beginning to grasp. The 750 galaxies JWST has shown us are not merely far away. They are invitations to think deeper, question more fiercely, and accept that our understanding of reality is still in its infancy. And as more data pours in, the universe is beginning to whisper the truth it has always held, that the story is far bigger, far more complex, and far stranger than we ever imagined. The implications of the James Webb Space Telescope's detection of 750 galaxies with unexpected complexity continue to deepen as the scientific community begins to confront the sheer magnitude of what this discovery entails. These findings aren't just a matter of astronomical record. They challenge the assumptions underlying our understanding of causality, scale, and the nature of existence itself. At the heart of this unfolding cosmic riddle lies a question that was once firmly answered by the Big Bang Theory. How did everything begin? The new data suggests the question may have been wrongly framed all along. To even begin unraveling this mystery, it's crucial to consider the underlying assumptions behind how scientists interpret the universe. Cosmological principles have until now relied on the assumption of homogeneity and isotropy, that the universe is roughly the same in all directions and from all locations. This assumption has served well under the Big Bang paradigm, providing a framework for interpreting redshift, cosmic microwave background radiation, and galaxy distribution. However, if galaxies are emerging with unexpected complexity, then these assumptions may need refinement. A universe that varies in its early development suggests we might be dealing with a cosmos that is more intricate in ways never previously imagined. One potential interpretation of this data is that we are witnessing an observable complexity from a more dynamic structure within our own universe, an internal configuration so complex it challenges our expectations. These structures could manifest through intricate cosmic processes, possibly influenced by unseen dynamics in such a way that galaxy formation appears accelerated. If so, then what we are observing as galaxies with unexpected complexity may reflect processes closer to home in a nonlinear configuration. This takes the conversation into the domain of advanced physics, realms where string theory, quantum loop gravity, and emergent spacetime theories operate. In these fields, the very concept of space as a static container is questioned. Instead, space is viewed as a product of relationships between quantum fields, vibrating strings, or information networks. The location of an object becomes a property derived from interactions rather than an inherent trait. In such a framework, galaxies might have formed through fluctuations in a quantum or informational fabric. The universe, then, may not be a balloon expanding from a central point, but a shifting, interwoven lattice where events and structures are bound by patterns rather than simple proximity. Another consideration brought to the fore by this discovery is the potential misinterpretation of redshift values. Redshift has long been used as a proxy for distance and velocity due to the expanding universe model, light stretching as space itself grows. However, if redshift can be influenced by other factors, such as interactions with exotic particles or complex cosmic conditions, then our measurements of cosmic distances and ages could be incomplete. These galaxies may not be as old as the redshift data suggests, but instead reflect unknown variables in the intervening space, throwing off our perception of both scale and age. This interpretation would affect our current cosmic timeline. Perhaps the universe formed mature galaxies faster under certain conditions, conditions we do not yet understand. Or perhaps our models are skewed by observational biases that the James Webb Space Telescope is only now beginning to uncover. If that's the case, then cosmology itself must undergo not a revision, but a reformation, one in which the rules of observation are as scrutinized as the data itself. Equally intriguing is the potential role of consciousness and the observer in the interpretation of these findings. Quantum physics has long held that the act of measurement can influence the state of a system. If this principle extends beyond particles to larger structures, if observation in some way interacts with the fabric of spacetime, then our detection of these anomalous galaxies might not be a passive act, but a form of engagement with the universe that produces novel configurations in response to our inquiries. It would mean that what we observe is not merely revealed by our instruments, but shaped by them, echoing the philosophical quandaries raised by participatory cosmology. The concept of a dynamic, responsive universe is deeply unsettling, but potentially enlightening. It reframes humanity not as passive witnesses to cosmic history, but as active participants in its unfolding. This line of thinking invites a new model of reality, one where physical structures and cosmological constants are co-generated through a dance of observation, interaction, and self-organization. In this scenario, the galaxies detected with unexpected complexity could be emergent phenomena, cosmic patterns catalyzed by the increasing precision of our observational technology. Taking a different approach, some scientists are now turning to thermodynamics and entropy as guiding principles in this cosmic puzzle. If these galaxies exhibit unexpected complexity, then the total entropy of the universe might be higher than expected. This